Let's continue on and keep looking at what makes these reciprocal trig functions unique. And so we're going to do a little bit of behavior exploration and thinking about how does sine behave, and therefore how would its reciprocal behave. So to do that, we're going to do a little bit of fraction review before we even dive into the graph itself. So if you do a like 1 over 1/2, what actually ends up happening is that's 1 divided by 1/2. And if we remember from our fraction math, 1 divided by 1/2 would be the same thing as 1 times the reciprocal, or 2. So 2. Versus 1 over 1/4 would actually be equal to 4. So when I'm considering which value is greater, that sort of fraction divided by the smaller fraction ends up being a larger number. So if I'm thinking about that mathematically, then something like 1 divided by 0.1 would be, 10, but 1 divided by 0.01 would actually end up equaling 100. So the smaller that number is in the denominator, the larger my actual numerical value ends up being. And so in this case, if I'm going from least to greatest, that 1 over 0.1 would be the smallest, and the next one would be the 1 over 0.01, and then it would go 1 over 0.001, and 1 over 0.0001, and then the largest one being that particular decimal. So what you should notice is, as the denominator gets smaller, the value of the fraction gets larger. And we can actually look even a little closer at it. So we said this was 10, this was 100, this would come out at 1,000. So this would come out at 10,000. And this would come out at 100,000. And if I kept sort of adding zeros to that decimal, this number would get closer and closer to infinity. So you could think about this as this approaches infinity. Now, what does this have to do with our reciprocal functions? Well, let's think about this, mathematically speaking. So we're going to just plug in some numbers and look at what happens. And for these, you can, pull up your Desmos graphing calculator. We're going to actually pull up our Desmos graphing calculator here. And so sine of 3, and so we can go here and we're going to do sine of 3. You would get 0.141. Okay. And if I did sine of 3.1, I would get a slightly smaller number, 0.0415. And if I did 3.14, I'm getting 0.00159. So what you should notice is my numbers here are getting smaller and smaller and smaller until if I actually put in the value of pi here, I would get 0. So the question is, what on earth is the reciprocal function doing as these decimals get smaller and smaller and smaller? Because if I actually go and I try and type in cosecant of pi, I'm going to get an error message on the calculator, which makes sense because if I did the reciprocal of 0, I would have 1 over 0, which, well, I can't take something and divide it into nothing. If I have 10 cookies, I can't split them into 0 parts. It just doesn't work. So this is undefined at pi itself, but what's going on as we approach that value of pi? So let's go through, and if I put in cosecant of 3, okay, well that's 7.086, okay, 3.1, I get a little closer to pi. Now my number's getting a little bigger, 4.9, okay, and if I got even closer, so I put in that 3.14, I'm now all the way up at 627.883. And if I got even closer, you could, you should notice that my decimal is getting larger the closer I am, or this value, the output's getting larger the closer I'm getting to pi. So as our sine graph approaches pi on the from below, our cosecant, our reciprocal values, are getting bigger and bigger and bigger. So this notation here, just to sort of get a sense of it, that little negative sign is just meaning we're approaching pi from the left. So we're coming from the left, so from lower values. Sine is approaching 0. As x approaches pi from the left, cosecant, though, is actually approaching infinity because we're getting that smaller decimal in the denominator of our fraction going on. All right, so what if we come and approach from the right? So just looking at the sine graph now, you should notice that these values, unlike our previous ones, they should all come out negative because we're coming from the left. So I did start with 3.2, so I got a negative 0.05, and then 0.15, that's a little closer but still above, so negative 0.008, and then negative 142. Notice negative still, but an even smaller decimal. And so just take a minute and predict. Yes, sine is still approaching 0. This time, you notice the little plus sign, we're going from the right. But what's going to happen when we look at the reciprocal functions? Well, knowing what we talked about on the previous problem, since sine is negative, I would bet cosecant is negative. And you should notice, okay, so we got negative 17.1. And then if I move to 3.15, I get negative 118.94. And 142, I get negative 2,454.9. So you should notice that our values are getting, and if I put in pi itself, we've already done that, that's undefined. Our values are getting more and more negative. So when that happens, we say the value is approaching negative infinity. Well, so if I just looked at this situation, what's going on here? Well, the cosecant graph, if we sort of fill it in, actually has what is known as a vertical asymptote there. So, one side of pi over 2 is approaching positive infinity while the other side is approaching negative infinity. And notice that's going to happen every time my sine graph approaches 0. And it makes sense because the same thing would be going on. So if we want to generalize, and I'm going to flip back to full screen here. If I want to generalize what's happening as sine approaches 0 to cosecant, I would say that cosecant of x would be approaching either positive infinity or negative infinity. And that would depend on whether the sine function is positive or negative. You could, and so this would be our generalization. It's getting infinitely large. So what this basically answer in part F is proving, and we sort of talked a little bit about when we looked at the graph, is that basically our graphs of cosecant have vertical asymptotes. And this is different than, our sine and cosine graph. Our sine and cosine graphs were continuous. We no longer have a continuous function. So instead, every time there's a vertical asymptote, is going to be when sine is approaching 0. So if I'm looking on the domain between 0 and 2 pi, when does sine of x equal 0? Well, it equals 0 at 0. And then it also equals 0 at pi. And then equals 0 again at 2 pi. So basically I only had us go from 0 to 2 pi, but we could keep going. We'd have another asymptote at 3 pi, at 4 pi, or we could go in the negative direction. And so we're going to have asymptotes sort of on those pi terms. If that's true because cosecant is the reciprocal of sine, well then you're going to get a similar relationship when you're looking at secant, because think about it, secant of x is equal to 1 over cosine of x. So we're going to end up with that sort of asymptote, those infinities, whenever cosine of x approaches 0. Well, cosine of x, so when does cosine of x approach 0 or equal 0? Well, it's going to equal 0 at sort of our, when our terminal ray hits that, the vertical axis. So that's going to be at terms like pi over 2 or 3 pi over 2 or 5 pi over 2, and so forth. So every time it sort of sweeps around to that vertical asymptote. So our justification here would be secant is going to approach positive or negative infinity whenever cosine of x approaches 0 and cosine of x equals 0 at sort of our pi over 2, 3 pi over 2, 5 pi over 2, whenever that sort of term next to the pi is odd. And this is just getting you a sense of sort of the interesting features of these reciprocal function graphs. They're not continuous, they look a little different, and so it's important to just sort of always think back to that, especially as we move into sort of solving equations with them and those sorts of things. All right, now we're going to sort of turn back a little bit and sort of go back to some of the ideas that we were looking at, and I'm sort of skipping back, that notion within the unit circle. And if we were given a point on the unit circle, what could we know about sort of our trig ratios? So I hope you wrote this down, because we're going to sort of be referring back to some of these ideas as we answer the following question. So we're given a coordinate point on a circle. This isn't a unit circle, and I know it's not a unit circle because those points are way too big. And I'm asked to sketch a circle with a terminal ray that intersects the circle at this particular point. I want to label the angle formed by the terminal ray as theta. Now, in this particular case, I like to do black for the coordinate plane. And I'm going to sketch my poorly drawn circle. So you'll notice my circle drawing skills are not perfect, but it works. And I want to point at basically 20, negative 21. Yeah, I don't know where that's going to be. I'm going to sort of make up a point. It's going to fall, somewhere down here because the x coordinate is positive, the y coordinate's negative. So we're going to call that point right there 20, negative 21. With this would be then our angle theta. Now, if I'm looking at this circle, there's some pieces of information I don't know. One of the first things I don't actually know is the radius length. I know clearly this isn't a unit circle because my point on the circle is further away than 1 unit. But I don't actually know how big the circle is. So I need to figure that out before I can do anything else, because remember, our sine and cosine value is measured in radius length. So if I don't have those radius lengths, then I can't figure out what sine is or cosine is. So I like to sort of, almost similar to what we had back on that first page, I'm going to draw in a triangle similar to this one right here from my coordinate point, and I'm going to label the side lengths I know within it, and then use that to sort of figure the rest out. So here's my vertical distance. That's negative 21. And then I have my horizontal distance. That's 20. And I have a pretty little right triangle and my unknown radius length. Well, within any right triangle, I can find the side lengths by using Pythagorean's theorem. So if you remember Pythagorean theorem, the hypotenuse squared equals the 2 leg lengths squared added together. So 20 squared plus 21 squared. And you might be going, but you dropped off the negative. Well, I dropped off the negative because if I square it, it's not really going to matter. So I dropped off the negative. I don't want r squared, I want r, so I would actually take the square root of this. And we should come out with a nice even 29. So the radius of this circle is 29. So if we're then thinking about finding the exact trig values for the following, trig ratios, sine, remember, is our vertical distance measured in radius length. So that would be negative 21 divided by 29 to get it as radius lengths. And we want to keep our answers exact here. So sometimes what you'll hear these referred to as is these are our trig ratios. And so, y over r gets me my sine value. Cosine, I'm looking at the horizontal, which was 20, measured in radius lengths, 29. And it should be positive because I'm, positive horizontal distance. Tangent is a slope. Slope is our sort of change in height, so that negative 21 divided by our horizontal change, 20, and a negative slope makes sense. Now to simply get from the first to sort of our reciprocal functions, we simply need to take the reciprocal of each of these. So in this case, flipping your fraction finds us the reciprocal of the original function. That would be 1 over the original fraction I started with. Here we get 29/20ths, and cotangent would be negative 20, our x over our y value. We want the exact values, we're keeping it. Notice I was never asked to figure out what theta was. I didn't need to find what theta was to answer these questions. It's just some arbitrary angle measure. In the last piece of this activity, we're going to be looking at using the other part of our reciprocal functions. So up here we are focusing on that coordinate point and the ratios we can get out of our coordinate point. The other piece is sort of using the idea, and I'm going to just sort of make a note at the top so that I don't have to keep going back to page 1, that secant of x is equal to 1 over cosine of x, and cosecant of x is equal to 1 over sine of x, and cotangent. So the relationships between sine, cosine, and our reciprocal functions, because what's going to happen is we may face equations that have cosecant or secant in them. And life is just much easier if I can get them written as a single trig function instead of multiple trig functions, and particularly if I could get them to be sines and cosines, because I'm very confident at dealing with my sine and cosine equations. So we're going to be sort of rewriting trig expressions to get that sort of simplified version. And simplified is a pretty arbitrary term, but for the sake of our explorations, we're going to be trying to get just one trig expression. So a good place to start is to rewrite everything in your trig expression as sines and cosines. So in this case, I have secant, and secant's equal to 1 over cosine of x. Now the next term is tangent. If we remember, tangent is a slope, and so up top we were thinking about that as y over x, but I can also think about that as sine of x over cosine of x. All right, then we're given cotangent, and remember, we're doing sines and cosines, so yes, that's equal to 1 over tangent, but I'm going to actually rewrite that as cosine of x over sine of x. I said earlier, I find that version a little more helpful. And then last but not least, sine of x. And I'm going to write it as a fraction just so I know that's in the numerator, not the denominator. Next step is we want to simplify if possible. And so this is remembering when we multiply fractions, we multiply the numerators and we multiply the denominators. Now, if I have something like a cosine divided by a cosine, I'm just going to make a little note over here. Cosine of x over cosine of x would just equal 1. They would, reduce each other out. So I think that's just going to be 1. And notice I have a similar thing going on here with sine of x and sine of x. So that would also equal just 1. Which means when all said and done, I have 1 times 1 times 1 times sine of x. and cosine times 1 times 1 times 1 over cosine of x. So sine of x over cosine of x, which is one of our trig functions. That would be the same thing as tangent of x. And so we started with 4 trig functions being multiplied. With a little bit of simplification work, we could get it down to just a sort of single trig expression, which makes life sort of easier to deal with. So take a minute, think about these sort of reciprocal we call these identities, these reciprocal identities. I want you to try the next few problems and then come back to the video, hit play, and then you can see how I did them. Okay, so we know that these problems are all going to come out as either cosine, sine, tangent, or cotangent, or secant, or cosecant. Like, we're keeping these should come out as a single trig function. Step 1, I always like to start, I'm going to try and rewrite this sine and cosine. One of ours is already written as sine of x, so that makes it easy. And then I'm going to times that by cotangent. And remember, cotangent, made a note up top, cosine of x over sine of x. So cosine of x over sine of x. And if I notice, I take a look and I say, ooh, I got a sine and a sine, these would reduce to 1. And so I'm really just left with cosine of x, my single trig function. All right, the next one, I have cosecant of x divided by secant of x. So this is going to require, and notice I said divided instead of a fraction. So I'm still going to rewrite as my sine and cosine values, but then I'm going to do a little bit of fraction work, which is hinted at in this sort of definition over here. So cosecant, remember, is 1 over sine of x, and that's being divided by secant of x, which is 1 over cosine of x. Now, I don't actually like keeping my fractions written this way because it's sort of complicated to see. So this is the same thing as saying 1 over sine of x divided by 1 over cosine of x. Now, when we divide by a fraction, we're actually multiplying by the reciprocal. So I really have 1 over sine of x times cosine of x over 1, which would be cosine of x over sine of x, which we talked about earlier is cotangent of x. So you can rewrite first and then deal with the reciprocal. Another option would be right off the bat, I could look at this and say I have tangent divided by secant of x. So, you know, I could think of this as just tangent of x divided by secant of x. And so this would be the same thing as sine of x over cosine of x divided by 1 over cosine of x, because secant is the reciprocal of cosine. Dividing is the same thing as multiplying by the reciprocal, so I'm going to have sine of x over cosine of x times cosine of x over 1. And I should notice, ooh, I have some simplification. Cosine divided by cosine is just equal to 1. And then I multiply across and I'm left with sine of x. So in all of these cases, we started with something that looked a lot scarier and got it down to this nice sort of simple single trig function. We're going to be working a lot more with this in the next module. So if you're like, oh my goodness, that seems so challenging, take a deep breath and you'll be okay. All right, the last 2-3 problems we're going to look at focus on solving with our reciprocal trig functions. So if we're given the value, finding those angle measures that would get us those values. So just like with some of our other ones, we're going to start with a sort of visual representation. So we're given that secant of alpha equals 3, and then asked, what is the value of cosine? Well, cosine should be the reciprocal of secant. So if secant is 3, and you could think that as 3 over 1, then cosine of alpha would be 1/3. And the reason why I had us sort of do that out, if I wanted to estimate where that might fall on the graph, well, I'm really looking where cosine is equal to 1/3. 1/3 would be about 0.3. So, you know, if this is 0.5, here would be 0.33333. So, you know, somewhere like here would be that x value. And so notice I'm just sort of giving a rough estimate of there's my cosine value. But for the sake of me knowing that cosine is an x value, is a lot easier to sort of draw in my estimates using you know, cosine versus sine. And then the same thing would be true with solving the equation. I'm very comfortable with solving equations that involve cosine versus dealing with equations that involve secant. So if I want to figure out the values of alpha, the actual angle measures here, you know, what is this angle versus what is this angle? If I solve this equation, cosine of alpha equals 1/3, whatever alpha values come out at 1/3 are going to be the same ones that make that secant of alpha equaling 3 true. So let's do that. So I'm going to use my inverse cosine, which we've already talked about as a function, you know, and where the limits on the domain are. And if I type in, you know, inverse cosine into my calculator, I come up with 1.2309. And so just like we showed here, that would be, I'm going to put it in a different color, that would be this angle measure right here in quadrant 1, this one. But I need to get the second angle measure. So remember, this angle down here, this reference angle would be, you know, the same measure, but that's going to be 2 pi less, you know, 2 pi minus that value. So 2 pi minus that 1.2309 is going to help me get that second angle measure. And if I put that into my calculator, I end up with a value of 5.052 as my second solution. And there's just the two solutions. And I could double check. If I went and I did, you know, secant of that 5.052 into, you know, Desmos, which allows me to do that, 5.052, you should come out with a number that's approximately 3. So check works. I'm really glad. But noticing that what made that possible was doing that rewriting into sine or cosine. So when we deal with any equations that involve our reciprocal identities, I would highly recommend that that's sort of the first step that you want to get to. I want to get my cosecant on one side so that I can rewrite this using reciprocal identities. So in this case, that would mean moving the 1/2 over. So I'd have cosecant of x, and I would times by 2, so equals 6. And if this was a sine or cosine function, I'd be like, well, cosecant, or, you know, sine can't equal 6, but cosecant can, because remember, cosecant is the reciprocal of sine. And so in this case, sine of x would actually equal 1/6, which is a total possible value. And just like we did with the previous problem, I'm going to use my inverse sine of 1/6, and I come up with, oops, not skipping ahead pages, 0.167. This gets me that angle in quadrant 1. And this is where, again, sine becomes a lot easier to deal with. I know sines are my y values. I'm going to have a matching angle in quadrant 2. So if this is that 0.167, then this is also 0.167. So to find that second solution, I would be doing pi minus 0.167, which would come out to 2.974. And so there are my two solutions. All right, next problem, we're given secant. I'm going to switch colors just so we don't get these mixed up together. So we have 4 times secant of x equals -2. So I need to get that 4 away so I can rewrite as a reciprocal. So I have secant of x equals negative 2 over 4, or negative 1/2. Well, the reciprocal of negative 1/2, and cosine of x is the reciprocal of secant, would be negative 2. But cosine of x has a range of negative 1 to 1. So can cosine of x ever equal to negative 2? No, it can't. So this would actually be not possible. And that's because if you go back, and we're going to actually take a minute to look at the graphs of, and I'm going to put in the graph of secant here just so we can see secant of x. You should notice that our graph of secant of x has this giant sort of hole in the middle of our range. So it won't actually ever equal values between negative 1 and 1, because when we're dealing with those reciprocal functions, there's just, since cosine can never be values above 1 or below 1, there's no way we're going to get fractions that are less than 1 or greater than negative 1, sort of in that in-between space. And so it's possible that when we go to solve an equation that involves our reciprocal trig functions, that they might just not have a solution. And this was one example like that. After completing this activity, if you sort of continue on to check your understanding, you'll get some more practice with these types of situations and problems.